overview over who we are, of course, explain the industry integrator project with an industrial use case, and then cut straight to the development results. Afterwards, there will be time for questions if any remain. Okay, the Innovator Institute is an independent commercial institution for applied science and research. We are located in the so-called Old Mold Roastery in Mülheim an der Ruhr in Germany. We are a team of 15 colleagues, 8, actually right now 10 engineers, 2 business accountants, 1 back office employee, 2 trainees, and 0 freelancers. Our USP is effective conversion instead of pure consultancy. This already shows that we are not a classic institution. However, if we are not a traditional R&D institution, what are we then? Let me put it like this. Our mission can be summarized in this quote. In an ideal world, every entrepreneur would be able to exhaust all reasonable and favorable opportunities even beside daily business. Okay, our approach to achieve this is threefold. First, we want to motivate small and medium-sized enterprises to make smart decisions and to to leap into innovations and changes. Furthermore, they receive intensive technical support from our engineers and partners. And last but not least, we support them by taking care of founding-related matters, so they can really dig into their core developments. Meanwhile, our ambition is to aim at the best possible outcome, and exceed it. Okay, so far we are engaging in funded developments on a regular basis. Here are some of them. Most of them are in a cooperation with local partners and focused mainly on practical approaches and customer added value. That's really the big point. For example, we developed a smart sensor buoy for effective water pollution detection and treatment afterwards. Maybe from the last conference turn in, I think it was in Sweden, you still know my shape memory alloy-based blow-pin project. And of course, the industry integrator we are talking about next. Okay, I guess that should do it for the preamble. Let's start into the use case. Okay, industry integrator. Beside other commitments, our biggest project is named Industry Integrator. It can be characterized, if you want to break it down, as a hub with the ability to connect large numbers of commonly used sensors with the aim to provide more transparency as a boost for black box systems, so you really know what is going on inside. That's meant on production facilities, industry processes, something like that. The development has the aim to enabling leaner and quality increased production with less carbon dioxide emissions. That's really the point. One of the sub-projects of the industry integrator frame is a smart tool for extrusion blow molding we are looking closer to. Okay, here's a little slide for between. For anybody who's not familiar with the production technique of extrusion blow molding, here's a short glance on the process. Molding, let me put it like this. Molded in tube-shaped plastic is clamped between two halves of a blow mold, like you just saw over there. The next step is by air pressure, like 8 to 12 bar. The tube gets expanded to the shapes of the wall and forms the cavity. After appropriate cooling time, some seconds, some minutes, depends. The finished item, for example, a canister, a bottle, whatever you want, can be ejected and the cycle starts all over again. Okay, so far so good, but yeah, what's the catch? In this context, the main lever for increased productivity is to shorten the cooling time. The cooling time has the biggest amount of time of the whole process, so there's our lever. This is typically done by improving the tool-integrated cooling system, so more water, whatever, so the cooling work better. However, a widely neglected potential is the optimization of the ejection timing. This is the point in which combines the shortest cooling period, so short cooling time, and simultaneously ensures the minimum needed stability of the somewhat cooled canister. If the time is not long enough, it's still very weak and will collapse. If it's cooled too long, it's pretty solid, but the process just took too long. It's not productive. So experience-based timing for the ejection timing is just a rough estimation and therefore not a therefore a potential source of waste, and should instead be replaced by objective sensor reading. However, so far there is no published extrusion tool available on the market with the possibility to really trace the temperature progression within the cavity. As it happens, we would like to present our approach of a sensor and logic integrated extrusion molding tool for direct process control. Okay, let's start it. It's all about cracking open the black box. It's about getting transparency inside the tool. So the approach is to gain insights into the hidden temperature behavior of the tool. Especially relevant are hotspots, which would result in issues in case of early ejection. It just would collapse, or would really, the quality would just not be fine. This happens because of uneven cooling rates due to different levels of wall distribution inside the cavity, meaning that certain parts of the article will require way more time to get solid than the thin parts. The job of the machine setter is to anticipate the required time to do exactly this. But that's, it's really just experience to ensure a safe production setup. The chosen ejection time is usually loaded with a proper safety margin. As this approach is reasonable for ensuring a troubleless production shift, everybody happy, but the production level suffers really big time due to unnecessary long cycles. Okay, so the question is how to close the gap between A and B. This is done by the integration of temperature sensors into the surface of the cavity. This hasn't been done so far, so it's a pretty interesting matter. As you can see on the right, I hope it's big enough, there are a couple of temperature sensors integrated directly into the tool. Some of them are highlighted in with cycles. There is the exact temperature of the down cooling item can be measured, which allows to set the perfect ejection point. So it's not knowledge-based. It's like, okay, the sensor says it's like 50 degrees, okay, it's time to open the mold. Meanwhile, a user-friendly dashboard shows all the temperature calculation within the mold. So you can see, where's it cooling down pretty good and where you have hotspots and everything like that. yeah, with this in mind, you can also look for weak spots of the cooling system and actually look on wall thickness distribution failures. Okay, yeah, of course, there have been some issues along the way. I guess which project doesn't have any issues. While the design of the controller unit went well, we struggled quite a bit with the integration of the NTC, so the temperature measurement units into the mold. Among other hurdles, delayed sensor readings presented the biggest problem, as the system responded just too slow to effectively control the process. This was solved by modifying the NTC's glass cover to a more dynamic response behavior. This was managed by precisely grinding down the drop-shaped glass cover, so the sensor itself to the sensor itself, so the distance, the measuring distance became smaller. And increasing also a very flat contact patch, so the sensor is really in touch with the article in the cavity. That's ensured a very low latency reading and helped to set up a fast control loop, and that's really what we needed. Another crunch point I can mention were the distorted measurement values caused by side effects of the very well working cooling of the tool. After different approaches, we decoupled the NTC heads from the cavity by using foamed ceramic compound, and that did the trick. So the cooling effect of the metal around the NTC doesn't anymore matter because it was isolated. Through this adjustment, the highly isolating compound shields the NTC from direct contact to the water-cooled cavity. And that actually enables significant higher accuracies of the measurement. Besides the, that was one too fast. Besides the heads of the NTCs, we also looked at the wiring. That was necessary because the wiring was parallel to the cooling system, and we got a cooling effect through the copper wiring into the sensor, and again didn't get the temperature of the plastic item inside the mold. But with ceramic tubes, we could conquer this challenge and got it into a level we could compensate by offset values. So it's we got a flat level. Okay, so what do we got? We have now a unique insight into the inner cavity. We can measure a former black box system, and that's really quite an industry innovation. We're also able to visualize the data for practical use, reduce needed cycle time, and therefore increase productivity and product quality, and of course less waste. A cool project bonus is the possibility to log the relevant parameters like, let's say, extrusion temperature, speed, the cooling curve, the ejection timing, timestamp. We can log that for each item. So in combination with a serial number label device, any kind, doesn't matter, you gain the high ability to item trace every item, which it's pretty handy for high security applications. What's next? The next step is to expand the approach to a related subsystem, like the cooling system, the extruder, the die head on the top. And furthermore, we would like to introduce different type of sensors, like pressure sensors for monitoring the inside pressure. And yeah, there are a couple more things in planning, and yeah, we hope to realize that as well. Yeah, all right. I think you got a good glance on the sub-project, smart tooling of our industry integrator. Yeah, if desired, I'm happy to answer your questions right now, or yeah, in short or more detailed via email. I'm pretty sure